My name is Michael Usolino, and I am a PhD candidate at the University of Colorado Boulder. And in this talk, I will be presenting training cascaded networks for speeded decisions using a temporal difference loss, which was work conducted as an intern at Google Research on the Brain team with Michael Moser and Sammy Bengio. At a coarse architectural level, conventional feed-forward networks and biological neural networks seem similar, but they have very different dynamics. With conventional feed-forward networks, layers operate sequentially, and each layer completes its computation before processing begins in the next layer. In biological neural networks, layers operate in parallel. Information transmission through a layer takes time, and layers broadcast their state continually, even as it evolves. In this work, we've explored a feed-forward architecture that has these biological dynamics, and we refer to this architecture as a cascaded network. We implement cascaded dynamics in a ResNet by replacing the standard ResNet block with a cascaded block. The block includes convolutional layers, depicted by block F in the figure, and we insert a new operator delta at the output of the convolution, which implements a tapped delay line memory. The memory is convolved with a temporal kernel, kappa, and we can choose this kernel to introduce various sorts of delays. Note that the skip connection bypasses the delay, which allows immediate transmission of primitive representations to higher blocks. As a result, all blocks contribute to the output at each time step, but the output produced by those blocks is based on partial or delayed information. The cascaded network is trained by unrolling it in time. Because it produces an output at each time, it can be trained to make speeded decisions, that is, to get the asymptotic output sooner. Toward this goal, we introduce a temporal difference cross-entropy loss. We use TD lambda, which specifies the target as a lambda-weighted exponential average of future outputs. Here, the pink curve shows the asymptotic accuracy for a cascaded ResNet 18 trained on SciFAR 100 over various lambda values between 0 and 1. Lambda closer to 0 significantly outperforms lambda closer to 1. This is notable because past temporal models have all used a method corresponding to lambda equals 1, which is simply training the model at each step to the target output. In contrast, lambda equals 0 corresponds to training at each step to predict the output at the next step, which encourages the model to reach its asymptotic state sooner. The orange dashed line is the accuracy of the standard ResNet 18, so the cascaded TD training loss improves accuracy of the model even when you don't care about the model's temporal dynamics at runtime. For SciFAR 10 and tiny ImageNet datasets, we also see best performance with lambda less than 1, but unfortunately, the cascaded model does not asymptotically outperform the standard ResNet, but does achieve comparable performance. The graph on the right shows the speed accuracy trade-off of our cascaded model in pink, the standard model run one layer at a time in orange, and a cascaded model that uses the weights from the standard model in purple. TD training produces a strictly superior speed accuracy trade-off. In the cascaded model, some instances are classified quickly while others need more processing time, and we find an interesting distinction between these fast and slow examples. In the left figure, the fast examples on the left appear to be more prototypical and have a uniform background, as compared to the slow instances on the right. We see this distinction between fast and slow in the cascaded TD model, but not in the cascaded standard model. The cascaded model has other nice properties as well, as it's more robust to time-varying input noise, and the temporal trace of outputs can be used to make what we call metacognitive judgments about the model's state, such as whether the input is out of distribution or when processing can be stopped. To wrap up, why should you care? The TD training procedure reorganizes knowledge in the ResNet, which affects accuracy of the trained weights, and it makes a deep ResNet functionally similar to a wide ResNet. This may inform the design of new massively parallel hardware. Thank you so much for your time and attention, and I hope to see you at the poster session.